Hello everyone, welcome back to another Civi 398 assignment tutorial. In this assignment tutorial, we're going to be covering assignment number 12, which is the big bonus question assignment. So this is actually going to be quite a challenging assignment, but you guys are really smart. I think that you guys can do just fine. Now, if you guys are saying, you know what, this assignment's a little bit too much, keep in mind it is a bonus assignment. You guys are not going to be required to do so, so please don't stress yourself out due to this bonus assignment. I don't want to see that at all. All right, so if we look at the bonus assignment here, it says masonry shear walls, which are shown below in figure 1, are a common structural solution to provide earthquake resistance in a structure. Due to the small aspect ratio of the walls, and the aspect ratio is the wall height divided by the wall length, the primary failure mode of these walls is due to shear, hence the name shear walls. So what does it mean by small aspect ratio? Well, if we look at these walls, they're basically square. They're not very slender like beams, they're very square. Hence, they take in a lot of shear. So as we can see here, this wall is developing a lot of shear cracks in both diagonal orientations. And this was a shear wall actually tested here at the University of Alberta. So now that you guys know what a shear wall is, we can go down and try and analyze one. So earthquakes are unique as they impose a lateral load within the walls by displacing the connected roof slabs above them, rather than creating defined, concentrated, and distributed loads. So this is actually a real problem when we deal with earthquakes, because what happens when an earthquake hits, it accelerates the base of the wall like this, and what happens is the floor slab above the wall starts moving back and forth. Now, this displaces the top of the wall, but the displacement, of course, isn't really connected to a defined load. Instead, we actually have a defined displacement. So, to be considered safe and serviceable, a masonry shear wall must exhibit a stiffness such that a lateral load of at least 1,000 kilonewtons is required to laterally displace the top surface of the wall by 3 millimeters. So this is actually going to be a key piece of information here once we're defining our loads in Abacus. The key here is that instead of putting on a horizontal force to displace this wall laterally, we are actually going to put a horizontal displacement of 3 millimeters along the top of the wall, and then compare how much force it requires to displace this wall 3 millimeters compared to the minimum stiffness of 1,000 kilonewtons. So this sounds really confusing, but I'm going to show you guys in Abacus how we do this. It's actually rather simple. Now, it says figure 2 depicts a 20 centimeter thick masonry wall, and this is important because at 20 centimeters, that is the in-plane thickness of the wall. Of course, we're going to want to know what that is once we're doing the modeling. It says that the wall also has a central opening and the wall is subjected to an earthquake load. Now, the earthquake load consists of a constant pressure of 0.5 MPa, so I'm going to highlight that, and actually I'll highlight constant pressure because that's going to be important, applied to the top of the wall. So as we can see in our picture here, we see that we have a pressure, a vertical pressure being applied to the top of the wall, and then followed by a horizontal displacement along the top surface of the wall. So if we compare the whole paragraph, what our loading scenario is actually consisting of is 2 steps. In the first step, we are going to apply a horizontal pressure of 0.5 MPa to the top of the wall. And then in the second step, we are going to displace the top of the wall by a factor of 3 millimeters. All right, so that's very important to keep in mind. Now, if we get into the actual question, it says use Abacus software and assuming plane stress conditions. So I'm going to highlight this. Plane stress conditions, you are required to A, determine the maximum opening size that the wall may feature while meeting the specified earthquake requirements. So if we actually look up here, we are given 3 different wall opening types. What you guys are expected to do is model each one of these and see if they meet the earthquake requirements. Now, we're going to talk very specifically what those earthquake requirements are once we get into Abacus. Now, part B says show the contour plot of the von Mises stress distribution for each opening size and identify the locations of potential failure within the wall. This is nice and easy because once you guys run the model, you guys are given that nice von Mises contour stress distribution. All you basically have to do is copy and paste it into your report and show me what exactly it looks like. Now, part C right here, this is going to be probably the hardest one for students, where it says determine the factor of safety against failure for each opening size. Now, this is a problem right here because we know that the wall resistance must be greater than 1,000 kilonewtons, but if we apply a horizontal displacement, Well, we know the displacement, but we actually don't know the load it takes to meet that displacement. So what we're going to have to do in part C is figure out, okay, if I displace the top of the wall by 3 millimeters, how much force is that actually going to take to create that displacement? And we're going to talk about that in Abacus as well. Now, finally, it says, assume that the openings are located in the geometric center of the wall and the base of the wall is fixed. So here's going to be our boundary condition. That's going to be very important. Ignore the self-weight of the wall. Well, that's explanatory because I never showed you guys how to deal with gravity loads in Abacus. Assume the material properties to be a linear elastic isotropic material with a Young's modulus of 15,000 MPa and a Poisson's ratio of 0.15. So here's our material properties. It also says assume that the material follows a von Mises failure criterion with the maximum stress being 20 MPa. Now, this is important too because let's say that we analyze our wall and it actually meets all of those earthquake requirements dealing with displacement. However, we have to check that all the stresses in the wall are less than 20 MPa. If it meets the requirements above, but the stresses in the wall are, say, 25 MPa, well, it doesn't matter that it met those displacement requirements because the wall actually failed before it did. All right, and then finally, the final thing says use full integration elements with a size of 100 millimeters. So this last statement right here, this actually has to deal with our mesh. All right, so I highly recommend that you guys have the assignment open while we go over this tutorial because I'm going to refer to these properties as we go through, and I don't want you guys getting confused where I'm pulling these numbers out of. All right, guys, I will see you in Abacus. Alrighty guys, welcome to Abacus. We've done many tutorials on Abacus already at this point, so I'm not going to go into too much detail about the kind of the theory behind everything or what everything means. I assume by this point you guys have seen my Abacus tutorials and you guys kind of know the basics. Now, of course, if something does need explaining, I'm going to explain it, but for the most part, I assume you guys know what's going on. So I've already saved the model, so I'm not going to get into that. So make sure that you save the model in a nice location, as well as set the work directory. As you guys are going to see in this particular model, setting the work directory is going to be very, very important. All right, guys, let's start with the model creation. So we know that the first part of Abacus is we want to define our parts. For us, we're lucky. We only have one part, which is our wall. So therefore, I can either click this button here to create the wall, or I can come down here into the parts and double click. And it's going to say, all right, what do you want to name this part? Well, let's call it our wall. And we know that we are dealing with a 2D wall, so I'm going to click 2D planar. And again, the approximate size, this does not matter at all, so I'm just going to click continue. So what I'm going to do is I'm going to work in millimeters, newtons, and MPa, of course, and I know that my wall is simply a rectangle. So I'm going to come over here to create rectangle, and it's going to want me to specify the bottom left corner and the top right corner. So I'm going to say the bottom left corner is at the origin, and my top right corner I know is at a distance of 6 meters horizontally, so 6,000 millimeters. And the height of the wall is at a distance 4,000 millimeters vertically, so 6,000, 4,000. And as we can see, this wall is quite big compared to our little grid down here. Again, this grid is what that approximate size means, but again, it doesn't matter because we can define points wherever we want. Now, I'm going to have a custom hole in the wall. So of course, you guys have 3 different openings in your wall that you guys are going to have to model. But for me specifically, I'm going to use a custom one that does not appear in any of your guys's openings. So if you guys are assuming this is going to be one of the answers to your question, it'll be a little bit, it'll be wrong, but this is how we do the process. So my goal here is to show you guys the process, not give you guys an answer to one of the openings. So I'm just going to pick this opening right here. Again, this is not one of the openings in your guys' assignment, so please don't copy me with this opening. All right, so we create the wall, and then you guys are going to create an opening, and once we're done, we can simply go done down here, and it'll give us our wall with our opening. So since we're only having one wall, we only have to define it as one part, and we can come down to property, and here is where we define the material properties of this wall. So again, I can click the button here, material property, or I can go down here to materials, double click, and it's going to ask us what we want to what do we want to name our material. So I'm just going to call this actually elastic masonry. because that's basically what we're doing. And of course, to define the elastic materials, we go to mechanical, elasticity, and then elastic. So of course, it's going to ask us for two things, which is expected, one of them being the Young's modulus and the other one being the Poisson's ratio. So we're given that our Young's modulus is 15,000 MPa and our Poisson's ratio is 0.15. So 0.15, good to go. I can go OK. And now if I expand the materials option, I see that I have a material defined called elastic masonry. Now, the next thing we have to do is take this material and apply it to the wall. And we do that by two things. First of all, creating a section. So right here, we have a create section button, or we can come down here to sections. It doesn't matter. And it's going to say, all right, you want to create a section, give it a name. So let's say masonry section. And again, we don't want to play with this. We're going to keep it solid and we're going to keep it homogeneous. So I'm just going to go continue. And it's going to ask us for two things. What material is associated with the section? Well, we know that's elastic masonry. And then it's going to ask for the plane stress / strain thickness. So again, this is that thickness into the page. And if we look at our assignment, it says that our masonry blocks are 20 centimeters thick. So we know that it's not going to be 1 millimeter thick. It's actually going to be 20 centimeters thick. And of course, since we're dealing with millimeters and not centimeters, we need to convert that to the equivalent millimeters. In this case, that is going to be 200. All right, so we click OK. And now we see that we have our nice masonry section defined. Now what we're going to do is we're going to take this section and apply it to our part that we created in the previous module. So there's a button for it right down here that says assign section. I'm going to click on that. It's going to say, where do you want to assign this section to? Well, of course, we know that we want to define it as this wall right here. So I'm going to click the wall, highlight it, and go done. And it's going to say, which section do you want to assign? Well, we only created the one section, so by default, it's going to be the only one we created. And we're going to click OK. So at this point right here, we can see that our part now turns into this seafoam color. I'm not even sure what seafoam is, but it was recommended in class, and that's the one I'm going to use from now on. So if you guys did it correctly, you guys will now have this seafoam green color part. All right, so this is how we created the part and then gave it the material properties as given in the assignment. But now we actually have to put this part into our actual model. So we go down to the module tab and we're going to go down to assembly. So this right here, this is our actual model. This is what Abacus is going to analyze. And of course, right now we have nothing in it. So what we need to do is we need to import our part that we created. And we can do that in two ways. One is right here where it says create instance, which basically means import part, or we can go down to the assembly tab here and double click instances. It's going to give us a list of parts that we've created, but for us, we've only created the one part. So we're going to click it and then we're going to go OK. Now, if we look at our model space, we have our wall here. It's nice and blue. It is ready to be analyzed. Now, before we do that, of course, we actually have to realize that we need to define both the boundary conditions as well as the loading of the wall. Now, this is where it gets very important because we know that our loading is actually done in two sequences, all right? Two sequences. First of all, we're going to apply that vertical pressure to the top of the wall, and then after the vertical pressure is applied, then we are going to start moving the wall laterally. How do we do that? Well, we come down into our step module right here. So if we actually look on the side, we have steps over here, or we can create steps using the button over here. So first of all, we want to create a step, and in this step, we want to apply the vertical load. So what I'm going to do is I'm going to call this vertical load, because in this step, this is where I'm going to apply the vertical load. I'm going to go static general, continue, and then from here, the only thing I'm going to be interested in is this NL-geom, which means nonlinear geometry. For the vertical load, we do not need to go into the incrementation at all. So for the vertical load, we are just going to stop here and click OK. All right, so now we have one step defined for the vertical load, but we know that after we apply the vertical load, we want to start displacing the wall horizontally. So I'm going to create a second step, and in this step, I'm going to call this one lateral load. All right, and it says, where does the step go after? Well, of course, this is going to be after the vertical load. And again, we are going to keep this as a static general step. All right, so nothing in this class will require any other type of loading procedure. We are always going to keep it static general. So I'm going to click OK. And by default, now that we have the nonlinear geometry on in a previous step, it will remain on for the entirety of the analysis. So I don't need to specify this as on again. However, we do want to deal with the incrementation. Now, this is something I kind of discussed in the lecture, but for those of you who were not there, what the incrementation is basically when does it want to analyze the load. So what happens is if I select 1 right here, this basically means that initially it's going to try and apply 100% of the load. So since I'm displacing this wall by 3 millimeters and I keep the initial as 1, what's actually going to happen is it's going to go from 0 millimeters all the way to 3 millimeters in one step. Now this is just fine, but the problem is all the data in between there we don't know. We'll have all the data for when the displacement is 0. We'll have all the data for when the displacement is 3 millimeters, but we'll know nothing in between. So what happens is we can actually limit this down here to create smaller step sizes. So instead of going right from 0 to 3, we can go from say 0 to 1 to 2 to 3, or from 0 to 0.5 to 1 to 1.5 to 2 to 2.5 to 3, etc., etc. So this right here, this is basically how much percent of the load you want to apply initially, and what is the maximum amount of load you want to apply per step. So what I'm going to do is I'm going to change this to 1%. So I'm going to change this to 0.01, and this to 0.01 as well. Now what's going to happen is instead of going right from 0 millimeters to 3 millimeters, it's going to apply 1% of 3 millimeters all the way until it reaches 3 millimeters. And just in case there is some unsuccessful incrementation, I'm just going to change this to 1,000, but you guys shouldn't actually need to worry about that. So just put it as 1,000. I don't think there's going to be any unsuccessful incrementations, all right? And I'm going to show you guys exactly what I meant by this 1% once we analyze our results. It's hard to picture right now, but once we analyze our results, it's going to be very, very clear. All right, so I'm going to go OK. And now in my step module, I can see 3 things. First, I have initial, which is what is my wall when no loads or displacements are applied. I have my vertical step, so right here I'm going to apply my vertical load, and then after that I am going to apply my lateral load. So once all those steps are defined, we can actually go into our load module and start defining all of these boundary conditions as well as loads. So we have 2 buttons here, create a load or create a boundary condition, or we can come down here and of course we have loads as well as boundary conditions. So what I'm going to do is I'm going to define them in the order they appear. So the first thing that we know is we have a boundary condition, which is the base of this wall is going to be fixed throughout the entirety of the analysis. Even when there's no loads applied to the wall, the base of the wall is going to be fixed. And because of this, we are going to put this in our initial step because again, the base of the wall is always going to be fixed. So I'm going to call this boundary condition fixed base. I'm going to come down here for displacement/rotation, and I'm going to click continue. Now it's going to say, all right, well, which part of the wall do you want to put your boundary condition on? We know we want it on the wall base. So I'm going to highlight the wall base right here. And then down here, normally we would go done because we have finished selecting. But for this particular question, we are going to want to create a set. Now, creating a set doesn't matter in terms of the analysis. What matters is in terms of analyzing the results. So I'm going to show you guys what happens when we create the set here. So we're going to click create set, and I'm just going to call this wall base. And once we analyze the results, it's going to become very, very clear why I'm creating this set down here. So I'm going to go done. And it's going to say, all right, what do you want to do to the base of the wall? Well, we know we want to restrain it from any lateral movement, and we want to restrain it from any vertical movement. Now, again, in these types of models, when we're dealing with these types of elements, they do not have a rotation degree of freedom. Therefore, we do not need to select any sort of rotational restraint. It's already done in the model. You guys can select it, but Abacus will give you a warning message basically saying, you guys don't need this. It'll still run the analysis just fine, but it will tell you, you guys do not need this. So I'm going to unselect it. I'm going to go OK. And now at the base of the wall here, we can see that it is restrained both vertically as well as laterally. All right, so if we remember our sequence of events, we have our fixed based wall, and then we want to apply a vertical pressure to the wall. So a pressure is actually considered a load over here. So we're going to double click load. It's going to say, all right, what step do we apply this load in? Well, we know we're going to apply this load in the vertical load step, and we should probably say what it is. So from here, this is an axial pressure, or you guys can call it vertical load. You guys can call it whatever you want. For shits and giggles, you guys can call it lateral load if you guys want. But remember that this is our pressure load, and the type of load it's going to be is actually going to be a pressure. So before we define things as concentrated forces, now we're actually going to define it as a pressure. So I'm going to click continue. It's going to say where on this wall do you want to define the pressure? Well, we know it's acting on the top surface of the wall up here. Now, just like before where it said create set, it's giving us the option to create a surface. We don't need to. If you guys do create the surface, it's not going to impact anything. I'm just going to not create it because I don't want to. I'm going to click done, and it's going to say, all right, how much pressure are we putting on this wall? Now, the sign convention for pressure in Abacus is this. If it's a positive pressure, it's going to be applied onto the object. If it's a negative pressure, it's going to be pulling away from the object. So even though our vertical pressure is going downwards, it's acting on the wall. So in this case, we have 0.5. And if I click continue, we see that our pressure is acting downwards onto the wall. If I were to go back to that pressure and go negative 0.5, what happens is the pressure actually changes so that it's pointing away from the wall. Of course, this is not true. Those gravity forces are going to be acting downwards onto the wall, so we are going to go simply 0.5. All right, so this is our second load that we applied to the wall. And we said after we apply that vertical load, then we are going to want to apply a lateral displacement. Now this is where it's going to get tricky for a lot of students, because if I were to click loads, there is nothing that says any sort of displacement. This whole load tab over here, this has to do with forces. So pressures, concentrated forces, gravity loads, stuff like that. So you guys are not going to find displacements anywhere in here. How to apply a displacement in Abacus? We actually have to go down to the boundary conditions tab. So what I'm going to do is I'm going to create a new boundary condition. And this right here is how I'm going to apply my lateral displacement. So the name of this, of course, I'm going to say lateral displacement. And down here, we want to put in what step we want to apply this displacement. Now, we know we're not going to apply it in our vertical load step because that's when we are applying our vertical load. We are going to apply it in our lateral load step down here. So we know it's going to be in our lateral load step. And the type of condition we are applying is a displacement over here. So I'm going to go continue. Just like before, it's going to say, all right, select which part of the wall you want to apply it to. While we know we're applying it to the top surface of the wall right here. So I'm going to click it. It's going to highlight, and I'm going to go done. And unlike the initial step where we just check off the boxes, in this step, since it's not the initial step, we can check the box that relates to it. So of course, this is a lateral displacement, so it's going to be in the U1 direction. So I'm going to check it. And then right here, we can put the value that we want to displace the wall by. In this case, we want -3. The reason why it's negative is because we're displacing it left when our positive sign convention is right. So if I go U1, check, and I go -3, I go OK. As we can see, what it's going to do is it's going to displace this wall to the left in our second step. All right, guys, so this is how we apply those boundary conditions, and we have to really keep in mind our steps over here. So I'm assuming you guys are good to go by now, and we remember that at this point, we are actually pretty good to run the analysis. We have our material properties defined, we've created our model, and we've applied the loads. The last thing that we need to do before we run the analysis is, of course, apply a mesh to the model. We want to apply a nice mesh so that the calculations are nice. Now, if you guys are doing research, this is typically one of the hardest steps because it takes a lot of trial and error to figure out if you have a mesh that gives good accuracy while maintaining a reasonable computation time. But luckily for us, in the assignment, it tells us exactly how big it wants the mesh. So again, to specify the size of the mesh, we come up over here to seed part instance. So I'm going to click that. And oh, this is trying to apply the mesh to the assembly. We don't apply the mesh to the assembly. We want to apply our mesh to our wall part. So make sure you click part before you try and seed it. So what happens is we're going to click seed part, and it says approximate global size. So this is basically saying how big do you want your elements? Well, in our actual question, it says it wants them as approximately 100 millimeters. So I'm going to put 100 in here. I'm going to go apply. And as we can see here, this will be the approximate size of our elements. So from here, I'm going to go OK. And then from here, now that I have seeded my part, I can go to mesh part. And do you want to mesh this part? Yes, I do. We're going to click OK, and we are going to get this. Now, if we look at this, this is actually pretty ugly because what we want our elements to be is rectangles or squares more specifically. But if we look at this, we can see that there's a lot of distortion happening around here. So what we do to try and fix this is we go to this button right here where it says Assign Mesh Controls, okay? Assign Mesh Controls. We're going to click it, and right here, it's using advancing front. We don't want that in this particular case. What we want is this one right here, the medial axis. So I'm going to click medial axis. I'm going to click OK. It's saying that you're making changes to your current mesh. Is it okay if we delete the current mesh? Yes, it is. We're going to delete it. And now what happens when I go back? There's still 100. But when I mesh the part this time, I go mesh part, OK. We can see that we actually have a very clean, nice looking mesh. All right, guys. So that's it so far. And the next thing that the question also specified about the mesh is it wants full integration. All right, so in order to do that, we go down to this tab over here where it says S4R, which basically means assign the element type. S4R, those numbers right there, that is one of the many different types of elements. So what we're going to do is we're going to click this, and we can see by default, it has reduced integration on. Now, when the question says that it wants full integration, what this basically means is we uncheck reduced integration over here. Now, the question also says it wants plane stress, but if we actually go into the family over here and scroll down, by default, Abacus will have this as plane stress, so we don't need to change anything there. All we have to do is uncheck the reduced integration. So I'm going to click OK. And right now, my elements are defined. They're approximately 100 millimeters, and they are full integration elements. So right now, we are good to go. So since everything is now defined, I can go down to the Analysis tab and Jobs, and I can create my job. So I'm going to call this simply Analysis 1, because why not? I'm going to click Continue. Again, you guys don't need to play with anything in the Analysis tab. We're just going to go Continue. And from here, we can see that we have Analysis 1 defined. Now, this is great because this is going to take our mesh in addition to all of the loads and our part that we've created and analyze them. So to do that, we're going to click on the job we created. We are going to right click and then go Submit. So what's going to happen is it's going to start submitting the file. Right here, it's converting everything that we defined in Abacus into a specific kind of a text file. And then that text file is going to get ran in the Abacus solver. So when it says running right here, it means that the file's been created and it is now running. And what we can actually do is we can right click and go monitor. So this right here will tell us exactly what Abacus is doing. So right now it's at 1.36. So this means it's at 36% of our target displacement of 3 millimeters. Then it got to 1.7. Again, this is basically what amount of lateral load we are putting on. So at this point right here where it's 0.88, this means that 88% of that 3 millimeters has been applied successfully. Now, if we look at warnings, this is just going to give you a warning saying that if we specify a plane stress / strain thickness not equal to 1, if we have contact, we have to account for that. Luckily for us, we don't have any contact, so we can just ignore that. So once our analysis is completed, it will say completed, and we can right click and go results to see the results. All right, so here's our wall. Again, this is the undeformed shape. If I want the deformed shape, I can click the button right here beside it that says plot deformed shape. And as we can see, it doesn't move too much. And that's, of course, because we only applied 3 millimeters of displacement when this wall is actually 6 meters long. So if you're looking at a 6 meter long wall and you're trying to find 3 millimeters, of course, it's going to be very hard to see. Now, what it's going to make this nice is we can plot the actual stress distribution. So if you guys remember in the assignment, one of the things it asks for is the von Mises stress distribution. This would be it right here. So you guys can just take a nice screenshot of that. If you guys want to, you guys can change this blue background color to whatever you like. You guys just simply go View, tabbed over here, go to Graphics Options. It says Viewport Background. We can go Solid, and then we can change our solid color down here to white. So I can go Apply, we can go OK. So if you guys are doing a Word document and you want to make your report look a little bit nicer, this is how you would do it. All right, so right now it's showing us the stresses after all of our loads have been applied. So at this point right here, our vertical load is 0.5 MPa, and the wall has been displaced by 3 millimeters. Now, the key to keep in mind here is that one of the requirements that we have for this wall to be considered safe is that the stresses in this wall are less than 20 MPa. Now, if we look at our von Mises stress here, we see that we actually have a stress of 20.6 MPa. So technically, this wall has actually failed. All right, so at this point, under 3 millimeters, this wall has actually failed. Now, the reason why I switched the incrementation in the step module for this lateral load is because we can actually go across and see how this load is being applied. So right now, this is the wall when the vertical load has been applied, but there is no lateral load. So what I can do here is I can click this button to go next, and we can see in this step time, this is 0.01, meaning this is the wall when 1% of the 3 millimeters has been applied. I can click again. We're now at 0.02. This is the stress distribution when 2% of the 3 millimeters has been applied. So we can keep going all the way on. And as we can see, this is going to be the stress distribution as we start displacing the wall. All right, so we can go on and on and on. So at this point right here, 0.5, this means this is the stress distribution when 50% of the 3 millimeters has been applied, or 1.5 millimeters has been applied. All right, so this is why I did the incrementation. It allows us to have a good idea of when the wall is actually going, because if I want to, I can monitor my von Mises stress up here to the point where it actually reaches that 20 MPa. So it's at it's at 18.6, 18.8, on and on and on. And we can see right now it hit the 20 MPa mark. Therefore, when the displacement is 97% of the 3 millimeters, let me just get my calculator out. I'm not the best at math. You guys can make fun of me. Where's the damn calculator? All right, so 0.97 times 3. This means that 2.91 millimeters of displacement has occurred when this wall actually failed. So this is why it's nice to see the step time over here. And of course, we can go to our last frame, which is our final frame over here. So again, when we're dealing with our assignment, we want to answer two questions. One is, at 3 millimeters, did the wall fail? In our particular case, our stress at 3 millimeters is above 20. Therefore, yes, our wall actually failed. Now, let's say that our stress limit was 25 MPa. If we look at this, we displaced 3 millimeters and all of our stresses are below 20 MPa. Therefore, 25 MPa if we're doing that scenario. Therefore, in that scenario, our wall is actually good to go. It didn't fail. Now, we actually have two requirements. The first one are the stresses below the defined stress limit. If it's 25 MPa, then yes, they are. Now we move on to the second thing, is saying, did the wall exhibit enough stiffness? Remember, when I apply the load here, I want to make sure that it takes a lot of load to apply 3 millimeters. Think of when you guys hold a ruler and you guys just push it with your finger. It doesn't take a lot of load for that ruler to bend. And we want the same thing for our wall, because even though it's good from a strength perspective, if you're in this building and it displaces a lot, well, you're going to be scared no matter what. It's not going to be comfortable for the people in the building. So what we actually have to do is we have to figure out how much load it takes to apply this displacement of 3 millimeters. Now, this is where it's going to get challenging and new for you guys. So in order to do this, we are going to look at the reaction forces at the base of the wall. And this makes sense because this wall is in equilibrium. Think of a cantilever. If I were to put a vertical load over here, Well, my vertical reaction over on the other side must be the exact same. So if I'm applying a load laterally on the top of the wall here, well, then my vertical reaction must be the exact same. So if I'm displacing my wall at the top here by 3 millimeters, well, the amount of load I'm putting on that wall is actually my lateral reaction at the base of the wall. So the question becomes, how do we know what this reaction force at the base of the wall is? Well, there's a couple things. So if we go up here, we can change our stresses to displacement, something like this. And if we were to go U1, which is our lateral displacement, we can see at the top of the wall, it is negative 3 millimeters, so that's good to go. But another option we have is this one right here, RF. What this means is reaction force. So if I want to, I can click reaction force, and I can go down and I can click RF1, which basically means the horizontal reaction force. So we can see at the base of the wall, there is a reaction force, and what we have here are just a bunch of values. Now, these values right here, this is not the reaction force. What happens here is this is the reaction force for one single node. So this single node is going to have a reaction force, this single node is going to have a reaction force, and the total reaction force is actually going to be the summation of the reaction forces of every single one of these nodes. So the question becomes, how can I retrieve that data and modify it to figure out how much reaction force I have? And this is where it's going to get new for you guys. So in order to do that, we are going over here. So right here, it says create XY data, which basically means in Abacus, create a graph. And that's what we're going to want to do. We're going to click it over here, and it's going to say create XY data. Where do you want this data from? What we are going to do is we're going to want our ODB. This basically means our results and our field output. So all of this information on the model on the contour plot, this is all field output. So we're going to click this right here. We are going to go continue, and we are going to get this menu right here, basically saying, what do you want to plot? Well, we know we want to plot our reaction forces at the nodes. So if we look right here, it says position, it says integration point. This right here, this is not a node. What we have to do is we have to switch this down here to unique nodal. This is where the reaction forces are going to occur. So we're going to click unique nodal, and we have a bunch of different options that appear, and we know we want to plot the horizontal reaction force. So I'm going to expand this here, and the horizontal one, of course, is in the one direction. Therefore, I'm going to check RF1. All right, so this is saying what variable I want to plot. But next we have to specify which nodes do we want to plot. So we have two options here. One is we can actually go into our viewport and select each node one by one, but we actually have a much nicer option. So instead of picking from the viewport, we can actually go down to node sets. All right, node sets. And remember when I defined that boundary condition at the base of the wall, I told you guys, create a set and call it whatever you want. In my case, I called it the wall base. And this is why, because instead of manually picking each one of these nodes, I can just click my set that I created, wall base, and if I were to go highlight in viewport, we can see it automatically selects every single one of those nodes along the base of the wall. Now at this point we're good to go because we said what variable we want to plot. We selected where what nodes we want to plot, so I'm going to simply select plot. And from here, I get this graph right here. So each one of these lines is a single node. All right, so of course, along the bottom of that wall, we have a ton of nodes. Each one of these lines is one of those nodes, just one of those nodes. So if I'm looking over here, this is the reaction force at one single node. And I know that the total reaction force is simply going to be the summation of all of these lines. Now, a lot of you guys may be saying, Clayton, why do we have two different lines? Well, keep in mind that we have two different steps. So all of this data right here, this is the reaction force of those nodes when we applied the vertical load. All right, so this is associated with the vertical load. That is from step time is equal to 0 to time is equal to 1. And then after we applied that vertical load, that's when we started applying our horizontal load. So from time is equal to 1 to time is equal to 2, this is our vertical load. And this makes sense because if we're starting to push the wall vertically, our horizontal reaction forces are going to start increasing. All right? So now the question becomes, I know that my total force required is the summation of all of these nodes. Well, how exactly do I do that? And we're actually not going to do that in Excel. Sorry, we're not going to do that in Abacus. We are going to do that in Excel. So what I'm going to do is I'm going to take all of this data and I'm going to transfer it over to Excel. So how do we do that? Well, we go to this tab right here that says Report. All right, so we're going to click Report and we are going to click XY. So from here, it says, well, which data do you want to save? Well, this is one node. This is another node. But of course, we know that we want all of the nodes. So I'm going to click the first one. I'm going to go down to the bottom one, and I'm going to select them all. So this makes sure that I have the data from every single one of my nodes. Next, we go into Setup, and it's going to say, what do you want to call the file name? Well, let's just call this wall data. So wall data, something like that, something that's very easy to identify. Next, you should select where you want to put your data. So what I'm going to do is I'm going to put this where I'm saving my model. So I have it in my Dropbox, I have it in YouTube, I have it in Civi 398, Assignments, Assignment 12, and Abacus. So if you guys actually look in here, these are all the Abacus files. I can see right here, this is my CAE, so this is my actual model. OBD, where is that? This one right here, this is actually my analysis information, everything like that. But what I'm going to do is I'm going to save my wall data inside of where all my Abacus files are, so I know where it is. So I'm going to click OK. It's going to update where you want to save it, and I'm going to go OK. All right, so at this point right here, we have all our data into a file. So I'm going to minimize Abacus over here, and we are going to look. So over here, this is where all my Abacus files were, and as we can see, we have a new file right here that is called wall data. All right, so what we're going to do is we are going to open up Excel over here, and oh, this is really bad because I this is actually kind of funny. This is because I tried to make Abacus nice and big. Of course, this looks really bad. All right, that's much better. Sorry about that, guys. I completely forgot that Abacus would explode on me and become really big. All right, so once we open up Excel, what we're going to want to do is we're going to want to open up that file we created. So we're going to go over here to the Open tab. I'm going to click it, and we're going to browse our computer. So this is why it's very important where you guys saved your file, because you guys are going to want to find it wherever it may be. Now for me, I saved it in the Abacus tab, and once we open it, we're going to see that the file is actually not there. So one thing to keep in mind is that when we're dealing with Excel, it's always going to look for Excel files to open. So what we do is we're going to come down to this drop-down tab, and instead of all Excel files, we're just going to go all files. And once we do that, your data should appear wherever it is. So I'm going to double click it, and then it's going to say, all right, we can try and open this up, but this isn't usually the format we're dealing with, so please make sure that we're doing it right. So what we're going to want is we're going to want to remain fixed width. We're going to go next, and then we're just going to scroll through all the data and make sure that there's no vertical lines through the middle of the data. And you guys may be saying, Clayton, what does that look like? Well, sometimes you'll have a line like this right through the middle of the data. Well, you're just going to double click it to make it go away, just to make sure that all the data looks really good. So after you guys done all that, you guys can open it up and you guys are going to get this, which is extremely overwhelming at first. All right, so I'm going to zoom in a little bit and show you guys exactly what Abacus gives you. Now your first column right here, this will always be the time. All right, the timestamps are loads. So remember that in our first step, which is from 0 to 1, this is when we applied that vertical load. Therefore, all of this data right here, this is going to be associated with the application of that vertical load. And since we don't really care about the vertical load, we're only concerned with that lateral load, we are just going to ignore this data. Now remember, our lateral load occurred in our second step, so our timestamp is going to be from 1 all the way until 2 down here. Now this makes sense to us, of course, because we specifically wanted this load to be applied in 1% increments. This is why it goes from 1 to 1.01 to 1.02 to 1.03, etc., all the way through. So this is the data that we actually want. Now, each one of these columns is the reaction force of one of those nodes, the horizontal reaction force of one of those nodes. So for instance, at this point right here, which is 1.1, or basically 10% of our lateral load, which is 0.3 millimeters, the reaction force of this very particular node is 1.73 times 10 to the 3 newtons. All right, so if we were to look at a horizontal row over here, this is basically all of the reaction forces at all of the nodes at the timestamp 1. All right, so what we're going to do is we said that what happens is our total applied lateral load is actually the summation of all the lateral loads of all of these nodes. So what we're going to do is we're going to come over to the side over here, and we're simply going to sum up all of those nodes. So in Excel, we can go sum, and I'm just going to highlight all of the nodes. All right, so this is going to give me the total lateral applied load for that specific timestamp. All right, so we're going to do that, and we're just going to carry this on down for all of the timestamps. So right now it's really, really small, but once we see that, once we get to the final timestamp, our load is actually quite big. Now, this is because we realized that when we're applying when we specified our units in Abacus, we defined them in MPa, millimeters, and newtons. Therefore, all of these forces are actually in newtons. So to convert to kilonewtons, we're just going to take our value in newtons and divide it by 1,000. This will give me the loads in kilonewtons. So I'm just going to drag this down here. And then we have our applied loads in terms of newtons. And we can see right here at our final timestamp, well, actually, let's do the timestamp first. It'll make it a little bit easier. So now that we have all the loads, what I'm going to do is I'm going to go loads, kilonewtons. We can also find our displacement in millimeters, because again, our timestamp, which is over on the very, very other side, this right here is the amount of load applied. So what we're going to do is we're going to take this value and minus 1 and then times it by our total load. So right here we have 1. 1 minus 1 is 0. That means that we have 0% of our load applied. 1.01 minus 1, that's 0.01. That means that 1% of our load is applied. So we can go on through that nice and easy. So what I'm going to do, go to this column. I'm going to create a nice formula. So this is equal to our timestamp, which is all the way over here. So in this case, it's 1. And what we're going to go is minus 1 times our total load. And in this case, our total displacement was 3 millimeters. So since right now it's 0, if I go down, this is the displacement associated with each one of these nodes. So this is exactly what we're going to look for. Now, when we come down to the bottom here, we can see that the load it takes to apply 3 millimeters of displacement, and actually let's zoom in on that even more. The load it takes to apply 3 millimeters of displacement is 1,340 kilonewtons. All right, and this is great because if we remembered our threshold, we said that the minimum load it took to apply the 3 millimeters must be greater than 1,000. If we look at our total load right here, we can see that 1,340 kilonewtons is greater than that 1,000 millimeter threshold. So in this case, our wall actually would be considered safe for the earthquake portion of it, or the ductility portion of it. Now, when it asks you guys for the factor of safety, all we're going to do is look at the total load it takes to displace the wall 3 millimeters and divide it by our minimum load of 1,000. So we're going to take that final load of 1,340 kilonewtons, and we are going to divide it by that 1,000 kilonewton minimum threshold. Once we do that, we can see that we get 1.34. So in this particular case, my factor of safety would be 1.34. Now, before concluding that this is indeed the final answer, remember that we have to check both this as well as the stresses. Once we check the stresses in Abacus, we actually saw that the wall actually failed because some of the stresses were higher than that 20 MPa limit. So because of this, we can say that this wall is actually not safe. The reason why is it failed the stress limit, even though it passes the ductility check. All right, so when you guys are doing your guys' reports, for each one of those wall openings, I want to see two things. One of them is the von Mises stress plot, and I want you guys to tell me if it actually fails due to the stress limit. The next thing I want you guys to do is I want you guys to come in here And I want you guys to tell me how much load it takes to displace the wall by a factor of 3 millimeters. And once we have that, I want you guys to tell me the factor of safety. All you guys have to do is take your total load and divide it by 1,000. All right, so that's basically it for this assignment. You guys just take what I did, repeat it 3 times, once for each one of those wall openings. You guys are going to be good to go. So I hope that this helped. I hope that this tutorial made it made it as clear as possible what's expected from this assignment. So I want to thank you guys all so much for listening. I really appreciate it. And I just want to congratulate you. This is the very, very last assignment of Civi 398. So congratulations, you guys did it. I'm very proud of each and every one of you. So again, thanks guys for everything this semester. It's been so much fun meeting you guys and talking with you guys, even though we haven't directly seen each other. All right, guys, again, thanks so much. I cannot repeat that enough. So thank you guys. I will see you guys in the final exam.